Hi, BC Calc. This is day 121. Today we are moving on a little bit from parametric to talk about polar area. So if you think back to the February review when we were really thinking about converting back and forth between rectangular and parametric form and polar form, that's where we're really starting to see a lot of those concepts come into play. Now, before we take a step away from polar, or from parametric, I should say, to get into polar, here's a question about finding the second derivative of a pair of parametric equations at t equals 1. So I think based on what we've done past 2 days with parametric, hopefully you can find that second derivative, evaluate at t equals 1. And then I said, this one, if you want, we can save for class. I mean, it's up to you. If you want to try it, you have the skills to do that at this point. Sorry, somebody's yelling outside. And then it says, find the surface area if we take this plane right here, this curve, and rotate it about the x-axis, what would be the generated surface area there. So if we had that all set, again, you could say that for class if you want. Let's get right into polar area. So today's goal is to find the area of an enclosed part or an entire part of a polar curve. So if we're doing just a certain section of it, what we're looking to do is find the area that's bound really by two different angles, theta 1 and theta 2. And we're going to do this for some polar graph r equals f of theta. And the derivation of this will be the following. We're going to relate this to what we know about graphs that are in rectangular form. So here's what we know about rectangular, right? When we find area under a curve, we break up our interval over a to b into small rectangles whose width is delta x. And that's how we approximate area. We find the sum of all the rectangles, take the limit as the number of rectangles goes to infinity, and that approximates the area under the curve in rectangular form, where each delta x is the difference of that interval, b minus a, divided by n, the number of rectangles. Well, in polar form, this is going to look a little bit different. But if we think about some sort of polar curve, r equals f of theta, and certainly take some time to get these diagrams into your notes. So we have some sort of polar curve wrapping around right here. If we want to find the area from theta 1 across to theta 2 over here, then what we're going to do is not break this up into rectangles, but we're going to break this up into sectors. Okay, so if we think about this as like a sector of a circle here, where this right here is some delta theta distance, then we would have that in polar, we're going to approximate by the area of a sector, where each delta theta is the difference theta 2 minus theta 1 divided by n. So just to kind of get a quick visual difference as to what we were doing in rectangular form with rectangles, that kind of makes sense, versus polar form with now we're breaking this up into different sectors. We're going to have to recall what the area of a sector is in order to eventually sum up the area of all of those sectors. And eventually, of course, this will turn into a definite integral. So area of a sector is the following. It's pi r squared, area of a circle, times the fraction of the circle that we're looking at. So times theta over 2 pi. And nicely, things kind of cancel here. The pi's cancel out, and we wind up getting the reduced form of the equation 1/2 r squared theta. Now, not that we've really thought about in degrees at all in our course this year, but theta must be an angle in radians if I'm comparing the central angle theta here to 2 pi. So just know that this formula really only applies if your angle theta is in radians, which we are always working in anyway. Okay. So if I then say, all right, well, what does r equal? R is the function f of theta. Okay, so it's going to be 1/2 f of theta squared, and theta is going to be in each case some delta theta that we're looking at. And what we want to do is, again, if this is the area of one sector, apply this to the area of all of the sectors that I break up over the interval from theta 1 to theta 2. Okay, so we can write that in some sort of fashion as a limit as n goes to infinity of the sum of all of the sectors with this area. And when you take the limit as n goes to infinity of this sum, that turns into the definition of a definite integral. So finally, last but not least, it's going to be 1/2. So you can pull that 1/2 out front. The integral from theta 1 to theta 2 of your function f of theta squared d theta. Okay, so it's actually going to be a pretty easy formula for us to use. I hope that derivation sort of makes sense in terms of taking an area of a sector, finding the sum of all the area of the sectors from theta 1 to theta 2 is this concept of the definite integral here. So what we're about to do is now let's get right into trying some practice here. Like for the first example, seeing the area enclosed by r equals 20 sine theta. So you're going to have to recall, and you can use your calculator here and there, but I'm hoping you remember what some of these polar curves look like. 20 sine theta, what does that look like? Well, when something has the form a cos or a sine theta, it winds up just being a circle. And this circle is going to have a starting place at the origin. What happens is as you plug in angles for theta, if it's a sine equation, the diameter is going to go up along the polar axis here. So if we plug in, let's say pi over 2, 20 times sine pi over 2 is going to be up here at 20. So it's going to curve around this way, and then eventually it would move back to where we started. So this value of 20 winds up representing the diameter of the circle. But here's what that looks like. So I want to find that area. Well, I'm pretty sure we know the area already, but we're going to confirm this with what we just used with our properties of our new area formula in polar. Well, what do we know the area to be? It's going to be pi r squared, where the radius is, okay, if the diameter is 10, the radius, or so diameter is 20, the radius is 10. So we know that the answer in the end, hopefully, will come out to be 100 pi. Let's check it out. So it's going to be 1/2 from theta 1 to theta 2. I don't know those yet. Of my function f of theta here, 20 sine theta squared d theta. Okay. So what I have to figure out is what are the bounds of integration? And to figure out those bounds of integration, you're asking yourself, when is the circle completed? So we started, like I said, at 0, 0. And what did I say when I got up here? I said, oh, I plugged in pi over 2, right? Because sine of pi over 2 would be 1. So I know that I got half a circle by pi over 2, which means we come back to 0 if I plug in pi for theta. That makes sense to me. So it turns out the bounds of integration here are going to be from 0 to pi. So that's one of the maybe the toughest parts at all of doing integration with polars. Just remembering to think about what the bounds are that either complete this cycle of a circle, okay, or in other instances when we start talking about other shaded areas, determining the bounds appropriately there. Let's go ahead and square this while we're at it. So that's going to be 20 squared, which is 400, sine squared theta d theta. Okay. A couple things I'm going to do in the next step. One of them being, let's pull the 400 out front to make that 200 out here, and then we get 0 to pi. How do we integrate sine squared? I mean, I guess it's been a little while, but we're going to see a lot more trig antiderivatives come up now. Well, sine squared, that's the one where you have to use the cos double angle identity to be able to rewrite sine squared. So sine squared is equivalent to, remember this, 1 minus cos 2 theta over 2 d theta. So if we make that substitution for sine squared, I can now do a few different things. I can actually pull the 1/2 out front and just integrate 1 minus cos 2 theta. So that might make my life a little bit easier. So I'll just do 100, 0 to pi, 1 minus cos 2 theta d theta. And let's go ahead and find the antiderivative at this point. So it's 100 times the integral of 1 d theta would just be theta. Okay, so make sure that we're using the correct variables here. When we integrate, the integral, it's going to be minus the integral of cos 2 theta. Integral of cos is sine, okay, but it's sine 2 theta with a u sub over 2. Okay, so don't forget about this piece that if you were to use u sub, you'd have to multiply by 1/2 to kind of keep that balance there. So sine 2 theta over 2 is what we get over the bounds from upper bound of pi, lower bound of 0. So this is going to be 100, and if I plug in pi here, I know theta is just pi, so that's fine. Minus sine of 2 pi. Well, sine of 2 pi is 0, so that kind of goes away. Okay, from that, I'm going to subtract. When I plug in 0 for theta, well, that's just 0. Sine of 0 is also 0, so this is just a big 0 when I plug in the 0 for the thetas. And therefore, lo and behold, we get 100 pi, which matches what we know about the area. So in the grand scheme of things, this is more of a direct route, but just showing you that if we go through the process that we derived for taking the area of those sectors, breaking it up into small pieces, finding the integral from 1 theta 1 to theta 2, we can derive that area in the same exact fashion. And of course, it's going to be useful for shapes that we don't have a definitive area formula for, like the very next example. So find the area enclosed by one loop of r equals 6 sine 2 theta. So do we remember what this looks like? I hope so. Something of the form a sine b theta or a cos b theta is called a Rose curve. And what do I know about this Rose curve? Well, I know that the max petal length, the max r value, is going to be the value of 6. And then if the frequency is 2 theta, that the number of petals of the Rose curve is 4. And the last thing I'm going to write down is that the first petal max is going to be at 45 degrees. And the reason I know that is that sine has the max at 90. But if the frequency is 2 theta, that means it's going to reach its max at 45. And I realize I should probably write that as pi over 4. Okay, so it doesn't really matter here. But yeah, at pi over 4, 45 degrees, that's where the max of the first petal is going to be. So if I were to make a rough sketch over here, some of the future lessons, by the way, have a nice polar grid for you to have some accuracy over. So there would be one petal at 45 or pi over 4, another 90 or another pi over 2 from there would be the next petal. Okay, you're going to get a polar curve that looks something like this. Not my best looking polar curve, but hopefully you'll understand here. All right, this is what I want to find. I want to find the area that's enclosed by one loop of that curve. Okay, so I know that I'm going to say that this is 1/2 the integral from 0 to, well, I know that this loop starts at 0, but how do I know when that loop is finished? Okay, so what do I have to plug in to get back to 0 again? Well, it turns out that, I know that the next place the sine curve would equal 0, if I think about a sine curve, is pi. But what am I going to plug in for theta here to make that come out to be a pi on the inside? It's going to happen by pi over 2. Right? If I plug in pi over 2 here, double that, you get pi. Sine of pi is back to 0. So that's when that first loop gets enclosed. We can find the integral from 0 to pi over 2. That's all we need to do for the bounds of integration. And then take 6 sine 2 theta, square that, d theta. Okay, so from there, let's keep going. So we've got 1/2 of 0 to pi over 2. This is going to become 36. And then sine squared of 2 theta, d theta. So we can clearly pull that 36 to the front and make this an 18, 0 to pi over 2. And then for sine squared, when I go to make a replacement here, we did sine squared a moment ago, right? It's 1 minus cos 2 theta over 2. So we're using that double angle identity. And notice how I doubled this theta when I replaced the identity with 1 minus cos 2 theta over 2. Well, the thing I want you to pay attention to here is we have sine squared of already a double theta. So when I go to make the replacement, I'm not going to write 1 minus cos 2 theta over 2. This is going to turn into 1 minus cos 4 theta over 2. And that's a replacement we've made in the past, but I think that can kind of play tricks in our mind a little bit. We're using a double angle identity to make this replacement. So we're doubling this angle right there to make it a 4 theta. Okay, so just be careful about that. Pull the 1/2 out front just like we did before, 9 from 0 to pi over 2. And now we just have 1 minus cos 4 theta on the inside. So we're up to the step where we can now integrate pretty easily, 9, and then we're going to get theta minus. This is the same thing as up above. It's just sine 4 theta over 4, though, from 0 up to pi over 2. So it's going to be 9 times, let's see, definitely pi over 2 there. And when I plug in pi over 2 here, 4 times pi over 2 is 2 pi. Well, sine of 2 pi is 0. Plug in the 0, and guess what? You get zeros in those spots again. So it's actually just pi over 2 minus 0, which is a final area. One loop has an area of 9 pi over 2 square units. All right. So we've got that. So if we wanted all four loops, I mean, that would be pretty easy. If I had said, what's the total area enclosed by the polar curve? We would have actually probably have set it up the same way, find the area of one loop and then quadruple it, right? So 4 times that area would be a total of 18 pi for the area of the entire polar curve. And this actually kind of sneaks its way back into tomorrow's lesson. So we're going to come back to the same exact example and think about that we know the area of the entire rose curve here defined by these 4 loops. We'll bring that back in a different context tomorrow. All right, last but not least, there is a question that we'll work on in class tomorrow. It is another AP question that has to deal with Taylor series. There's a little bit of error mixed in here. So we'll work on this in class tomorrow along with anything else we left blank. But today is a good introduction into polar area. Like I said, more to come with this. Have a great rest of your day.